Welcome to week 12 live session of molecular spectroscopy of physical chemist perspective. This is going to be the last live session that we are conducting, and today we are mainly going to discuss the coupling in NMR, nuclear magnetic resonance, coupling between the equivalent nuclei and non-equivalent nuclei. Yesterday, the day before the yesterday on Sunday, actually we had an extra session where we have started discussing in the lecture materials from week 11, and where the NMR has been taught by Professor Anindra Datta, and we have cleared some basic things, and we ended just before the coupling between of a AX kind of system. So in NMR, what we usually do, we use a radio frequency to see the transition between the nuclear spin states, and almost equivalent to the rotational line, the rotational or electronic spectroscopy in terms of qualitatively, not quantitatively, obviously, but there are some separate uh, things are also going on, and obviously the energy levels between these spin states are very less. That is why you need a radio frequency for NMR spectroscopy, nuclear magnetic resonance spectroscopy. So right now we are going to discuss the coupling, the quantum mechanical treatment behind the coupling. So let us start with that. AX system. Why AX system? Where these two proton, or I will not say proton, but two nuclei are actually now they are denoted as A and X. And why AX and the alphabet? Because A and X in the alphabet have a very large distance, right, between in the alphabet. By that, what we are trying to say that two hydrogens are actually placed in two different uh, electronic environment or chemical environment, where it is also we are providing you a fact that your shielding constant for A is very less than shielding constant of X, and due to that what will happen that the spin flipping, or the in other words the effective magnetic field faced by the A nuclei would be much more than the X nuclei. That is why the energy gap between the two different, or the different levels, alternative levels, will be higher for a nuclei than the X nuclei. Anyway, so in a AX kind of system, you expect to have, so this is a two spin system, right? So you expect the wave function to be something like alpha for A, alpha for X, then you expect alpha for A, beta for X, then you expect beta for A, alpha for X, and both are beta, A and X. So right now we don't know the relative energies, but so what is the energy operator Hamiltonian when there is no coupling? So that time the energy operator or the Hamiltonian, unperturbed Hamiltonian, is given by the individual energies of the spins, which is also given by gamma, which is gyromagnetic ratio, multiplied by your external magnetic field, and obviously there is shielding is associated. So this for the A nuclei and IZA, and same for the second nuclear. Why I am taking only the Z component? Because eventually it is going to give you the MH kind of component, which the nuclear quantum numbers or different spin state, and you will get the energies, right? So that is why we are working with only the IZX, Z small. So what would be the energy of this alpha A, alpha X kind of system? So you know energy is a expectation value, expectation between. So you will get it by, so energy of unperturbed energy alpha A, alpha X would be written in terms of psi 0. So you know that your energy, so this is how you get your expectation energy, right? So I will not write this thing, I will just directly write it. Today we will do a lot of derivation. Actually we are doing this because the first part is discussed by sir, the second part is also discussed, but the thing is sir has shown the presentation file which in video I was also unable to see the display the presentation. So if I can derivatize it here, then you can use it as a note, right? So that will help. So it will be alpha A, alpha X, and obviously then your gamma B0, 1 minus sigma A. As we have to do a lot of derivation, I might use some step jump, and I will tell it that if I have done any. Okay? Right now I am writing it whole alpha A, alpha X. So this is going to be the energy, unperturbed energy for your alpha A, alpha X, right? So that would be, so this minus gamma B0, this part will come outside. I can even break into two uh, uh, integrals, right? So I will prefer to do that, 1 minus sigma A, right? So then alpha A, alpha X will be on the bra, and in the gate it will be IZ will be operating on IZ will be operating on IZA will be only operating on the A nuclei, not the X. Vice versa, X will operate only on X, not A. That will be that will be level. So the first IZ when operating on the whole thing, so it will give you H cut by 2. Alpha A will remain alpha A, and alpha X will remain alpha X because the operator doesn't work on that, right? So we'll write it down in the next part. Now only IZX only operate on the alpha X, not alpha A. So alpha A will be remain as it is, and you will going to get H by H cut by 2 alpha X. Okay. So here I will give you a few cheat codes. You can say it like that. That an IZ operate on alpha, you are going to get H cut by 2 alpha. When IZ operate on beta, you are going to get minus H cut by 2 beta. And if I give you something earlier, because we are going to need it sometimes later, then this when IX operate on alpha, it will give you H cut by 2 beta. So the spin states are changing because these are not eigenvalue equations. And then Ix when operate on beta, it would give you H cut by 2. There is no change in sign, but the spin state will. What about Y? Y operate on alpha will give you something different. Now this I imaginary term will come, I is cut by 2 beta. So this is also not an eigenvalue equation. Iy operating on beta actually will give you minus I h cut by 2 alpha. So these are the formulas we will require in the due term. So that's why I kept it here. But let us come back to the derivation we are doing. I guess there is an issue with the Google Meet link, might be. I will just go and I will make it stay in the call. Okay. So these are for those who join later in our Google Meet discussion link. Okay, so let us do this. So as you can see, alpha a, alpha x, alpha a, alpha x. So you can think of a two integrals, right? Product of two integrals, and alpha a will be multiplied by alpha a, alpha x will be multiplied by alpha x, and as you can understood that this is going to be an normalized condition, and only h cut by 2 will come up, rest of the thing is 1, right? So for the first part it will be gamma b0 1 minus sigma a h cut by 2, and the second half gamma b0 1 minus sigma x. Similarly h cut by 2 will come up, rest is normalized case, right? So we can write it in terms of gamma b0 h cut 1 minus sigma a minus sigma x by 2. Okay? So this can be the first energy of this. We don't know yet that what is going to be the energy, the relative energy. What would be the energy for, say, beta a, beta x? So it will follow a similar manner, right? So if you see, I will just write the first term, so you will get the idea. Beta a, beta x minus gamma b0 1 minus sigma a I z a plus 1 minus sigma x I z capital X operating on, in the case it is beta a, beta x, right? So if you see, all the things are same. In this case, both the spin are same. So what do you expect? So you are going to expect a similar thing, right? So I will just write it. But in what will happen? Here the beta is coming. So you can see that minus is going to play a crucial role. Here Iz beta, when it operates on beta, it will give you minus h cut by 2 beta. So at least let me do this, or it may not be clear to you. So I have made a step jump beta x, and IZA is going to operate on beta a, beta x, and the next is also gamma b0 1 minus sigma x beta a, beta x IZX actually. X operate on beta a, beta x. But I was trying to say that it is going to give me 1 minus sigma a, beta x, Iz on this is going to give you minus h cut by 2 plus, so it will operate on this, not x, so it will give you a minus h cut by 2 beta a, beta x, right? And here also you are going to get gamma B0 1 minus sigma x. So Izx will work on beta x and will give you minus h cut by 2, right? So eventually it will be, so this is your one normalized condition, so both are plus, so actually we are going to get plus gamma b0 h cut. The rest of the thing are same with previous one, just the sign has changed. So now we will also want to know the energy of alpha a beta x, right? For that, let me take gamma b0 at beginning. I will take this outside. Inside, what do I have? I have 1 minus sigma a I z a plus 1 minus sigma x I z x operating on alpha a beta x, right? So we will get gamma b0 alpha a beta x 1 minus sigma a. So I could have take this thing outside, so I will do the same thing I have done earlier, else it may confuse you. Alpha a beta x I z a operating now on alpha a beta x gamma b0 1 minus sigma x. This sigma shielding constant, don't forget about that. I z x alpha a beta x. Okay. So now when IGA operate on alpha A, that will give me h cut by 2 only. So I will get h cut by 2 1 minus sigma A and alpha A beta x alpha A beta x, right? Then here in this case what I will get gamma b0 1 minus sigma x, and when IGX operate on bx beta x, I am going to get minus h cut by 2 and I will get eigenvalue equation, right? Then case alpha a beta x. This individually, this is a product of two integration, so this is going to be 1, right? So here I got gamma b0 h cut by 2 1 minus sigma a. Here also I got gamma b0 h cut, but I have plus here h cut by 2 1 minus sigma x. So in general I have minus gamma b0 h cut. If I take this thing as common, then I have 1 minus sigma a minus 1 plus sigma x, which is nothing but minus gamma b0 h cut sigma x minus sigma a divided by 2. So similarly, you will be able to show for alpha for x and beta for a, or I should write the usual way I was writing earlier, that is your beta A and alpha X. So that is the similar thing, right? Gamma B0 beta A alpha X 1 minus sigma A I Z A plus 1 minus sigma X I Z X, and then beta A alpha X. So as you saw from the earlier result also, similar thing you are going to get. You are going to get gamma B0 H card. Just the sign will change. The rest of the things are going to be same. Why did the sign change? Because now your A has beta spin. That is why you are going to get in this term minus will come forward and plus will be there. Earlier it was reversal. That is why you are getting an A like this. Now this is a case when coupling is not taking place. So what do you think? Whose energy is higher? Whose energy is lower? So when there is no magnetic field, then all these four states were degenerate. Now when the magnetic field is there, now due to presence of this magnetic field, now you all these four states have different energies. Now we have defined that your fine sigma A is less than sigma X, right? So this is a positive so this is a negative quantity altogether, and this is a positive quantity. Same for this also. This is a sigma A minus sigma X, which is going to be a negative. 1 minus negative, it will be a positive quantity. Overall it is a negative quantity, and this is also a negative quantity, right? So from here, if you want to draw energy of this, so the energy will follow of the spin states are as follows. This is in presence of magnetic field, but not in presence of is your energy scale. Now this is your topmost energy, which is beta 1, beta A, beta X. Your most stabilized is alpha A, alpha X. Now you got the idea that your this pin, the second one. So this is one, this is under two. The two state is the first excited spin state would be alpha A, beta X, and third would be, because these are having minor in, they have stabilized and they are destabilized. This is beta A alpha X. Okay, so now if you consider the one photon rule and see the transition, then you are going to see what transitions are possible. One transition from 1 to 2 is actually the change in the spin of X. So alpha X is going to change to beta X, right? What will happen if you go from 1 to 3? It is alpha A will change to beta A, right? Same when you go from 2 to 3, there is a change in the spin of alpha A to beta A. 3 to 4 is alpha X to beta X, right? And what are the energy differences? Suppose the energy difference between E2 minus E01 that is related to the spin reversal of X nuclei is nothing but you got the values, right? So the second one is alpha X, alpha A, beta X. So the energy is minus gamma B0 each cut sigma X minus sigma A divided by 2, right? And you have the energy for alpha A and alpha X, that is also minus, right? So minus minus plus gamma B0 H cut 1 minus sigma A plus sigma X divided by 2. How much is this? So you have gamma B0 H cut. Then I am taking this minus into inside, then it will be sigma A by 2 minus sigma X by 2. Then it is 1 minus sigma A by 2 minus sigma X by 2. So if I show you, then your sigma A by 2 and these are going to cut, and you are going to get gamma B0 H cut 1 minus sigma X, and that is nothing but your energy difference between the spin state of X nuclei, right? That is H into your Larmor frequency related to the X nuclei, that is H nu X. And you can show it that this is going to be equal to the unperturbed fourth energy minus the unperturbed third energy. That is also related to the spin change of X. What about the second third gap between third and 1? So that is plus gamma B0 H cut sigma X minus sigma A divided by 2 plus, this is not going to, this is going to be plus because plus gamma B0 H cut 1 minus sigma A plus sigma X divided by 2. Similarly, we are going to see if I take this thing as common, I am going to get sigma X by 2 minus sigma A by 2 plus 1 minus sigma A by 2 minus sigma X by 2. Now your sigma X, this term is going to sigma gamma B0 H cut 1 minus sigma A, and this is related to the energy difference between the spin state of A nuclei. And eventually you can show that this is also equals to the unperturbed fourth energy minus unperturbed second energy. Okay, and due to this, what kind of spectra you expect? If this is your spectra and your Larmor frequency is this side, then obviously you can see the energy gap between the nuclear state spin state of A is more than X. That is why you expect two signals. So you can see there are four transitions, but two of them are equivalent in each cases, and that is why you are going to see two spectra, one related to sigma X and one not sigma, I mean nu X and nu A, right? This is the case when the, so I'll write it here also. This is the case when there is no perturbation, there is no spin-spin coupling in A and X. Okay, now we will consider a situation where there will be spin-spin coupling, and this spin-spin coupling is so this coupling is actually will work as a perturbation. So this why perturbation? Perturbation is very small change in the system. It is not like that. It is the external magnetic field. That amount of magnetic field it is not going to generate. It is going to affect very minutely. That is why we are treating it as a perturbation system, and you will see the correction or you will see the change in the energy will be will be equals to the first order perturbation term. So I will write it here. Coupling will act as a small perturbation. Actually, I should not write small perturbation because perturbation actually means this is a small, this small. So first order, and we will consider only the first order perturbation. Energy correction is given by this. So this is your perturbation, and these are your unperturbed ground state wave functions. Actually, your Hamiltonian has now become your unperturbed Hamiltonian, sum of these and this perturbation, first order perturbation, and your energy has become unperturbed energy plus this first order perturbation. And this is given by this, and we are trying to see that what is the value of what is this perturbation or how much energy correction have been taking place. So we have already assigned the states as 1, 2 and 3. So we will see that what is the change. We will start with, and here the actually this perturbation is given by, in case of coupling it is given by h by h cut square JAX, which is the coupling constant, and multiplication between the spin vector of A, this is the dot product, and this dot product inside this actually will lead to IAIX of x coordinate, then IAIX of y coordinate. Look that I am keeping the coordinate at small letters. Then IAIX at z. Okay, so this is the dot product, and these are going to be constant. It will not work on the wave function, so I'll keep it outside. So let me show you what the first one is going to be. It is going to be, I will take as it is going to be a constant, so I'll keep this outside. Psi 0 you already know, alpha a, alpha x, and then I have defined it that this is going to be that, so I will write it once. Okay, then IA IX, then I, obviously these are operators, and it will operator. So obviously what you can do, you can break it into the three things, but I will try to do it together. So alpha x is going to operate on alpha a, and alpha xx is going to operate on alpha x. So I will write those formula again here, that ix alpha will be given by h cut by 2 beta, not eigenvalue equation. Ix on beta will be h cut by 2 alpha. There is no change in sign but change in wave function. Iy on alpha is going to give you ih cross by 2 beta, iy by beta, h cross by 2, ih cross by 2 minus ih cross by 2 alpha. Iz by 2 alpha is the only eigenvalue equation, and along with Iz on beta, that is going to give you minus h cut by 2, but give back your beta. Okay, so Ix, when it is operating on alpha a, it will give you beta a, but h cut by 2 beta a. What about when it is working on alpha x working on alpha x, it is going to give you beta x, right, along with h cut by 2. Then when iay operate on alpha a, it will give you ih cross by 2 beta a. When ixy operate on alpha x, it will going to give you same ih cross by 2 beta x. What about z? Z's are relatively easy. Eigenvalue operation equation, h cut by 2 alpha x. So h cut by h cut is square jax alpha a alpha x, first is h cut square by 4 beta a beta x. Obviously you can see a when you try to do the integration between these two, these are not normalized, these are orthogonal wave functions, so it is going to give you 0. Same for, so let me at least write it like this many h cut square jx. So I am splitted those things into three different integrals, alpha a alpha x. Now this is going to give you I h square, this is going to be minus h cut square by 4, right? But still it is going to give you beta a beta x. So obviously this is also going, this integral is also going to be 0. What about the last one? Last one is h cut square by 4. I have made one mistake. I have not shown you the common thing. So that is obviously h by h cut square by 4 jax alpha a alpha x, h cut square by 4 alpha a alpha x, right? So as you can see, so this is 0, this is 0, but this is 1, but this will come outside, so it will be only h by h cut square jax h cut square by 4 1, and that is actually nothing but h jx by 4. So your alpha a alpha x is destabilized by So similarly, you can show for the E4 correction to the fourth state is going to be same, because you see on all the spin states are similar, right? Beta A, beta X, right? So the first two terms are going to contribute nothing, because the beta A, beta X are going to become um, something else due to the operation on operator ix and ib. Beta will become alpha, alpha will become beta will become alpha, right? Beta a will become alpha a, beta x will become alpha x. So those are not eigenvalue equations. So from those terms you are going to get 0, but only with the iz operator you are going to get something, and that is this. So your beta a and beta x is also going to destabilized by EJAX by 4. What do I mean by destabilized? Actually, your energy of these states is going to increase. Increase by this factor, 8, not factor, but this amount, HJAX by 4. Actually, by factor means always it you multiply, but here it is adding up. HJAX by 4, energy is adding up. Okay, now let's see what will happen corrected terms of energy due to coupling on E2 and E3, right? So we will take this out, h cut square JAX. Your unpart of wave function is alpha A beta X, right? And then obviously IAX, I made one mistake, I guess. So I will just change a few things here and there. It will not change the whole thing, so that we will be in a same order, because as you can see here I was writing IZA. So I'll sorry, here I was writing the right thing. Okay, here it will be small x A, small x capital X, small y A, small y X. So we are going to follow this convention, right? So I X A, I X capital X, I Y A, Y capital X, Z A, Z capital X. Okay, same here also. A X capital X. I will split it right now before going to the next, that is h by h cut square JAX, then it is IYA, IYX, alpha A beta X, plus another term would be h by h cut square JAX, alpha A beta X, IZA each of these integrals will yield. So xa when operating on only going to be operating on alpha a, and that will give me h cut by 2. Obviously it will give me beta a, the wave function will change. Similarly for this alpha a, obviously you can see the it has changed, so it is going to give me 0 integral, so it is orthogonal. What about the next one? Iy, when it operates on ia, it is going y operating on alpha is going to give me ih cut by 2, and it will change the sign, right? Change the sign, not the sign, but change the wave function. What about when iy operate on beta? That time you are going to get minus ih cut by 2 alpha x. Obviously sign will change, also the wave function. And again you see this is a orthogonal condition, so overall this is going to give 0 because alpha a beta x integrated with beta a alpha x. So those are orthogonal wave functions. Only this term is going to survive, x, that is alpha a beta x h cut square by 4. I will write it directly, alpha a beta x. Only change is here, it will be a minus. Why minus? Tell me why there is a minus. Because this, so I will write it in steps. I have not done steps here. It's not a big step jump still. So when I z a operate on alpha a, you are going to get h cut by a alpha a. When I z x going to operate on beta x, it is operating on beta, so you are going to get h minus h cut by 2 beta x. That's why overall you are going to get h by h cut square ax. Obviously I will not write this, I will directly write minus h cut square by 4, and rest is, I will write it once maybe, alpha a beta x, alpha a beta x. This is a normal condition, so you are going to get minus h j a x by 4. So your second energy level correction is this. So your this state, that alpha a beta x is going to stabilized by this amount. Okay. Similarly, obviously I will not do this calculation again, but you will be able to show that E31 correction would be minus h jx by 4, right? Because if you do that, obviously the first two terms due to ix operator and iy operator are going to be 0. Only you are going to get something from the iz operator. Again the wave functions are alpha sorry beta a alpha x, so beta will going to give you some minus beta a, right? So due to that, again you are going to have this minus factor, and your uh, beta a alpha x is also going to stabilized by hj. So I will draw this thing again. So no spin coupling and spin coupling, two states. Two conditions, right? This is your energy scale. Earlier it was your beta A, beta X, the fourth one, right? Then this was our third one quarter. It is beta A alpha X. The second one was there, alpha A beta X, and your ground one was there, which is alpha A alpha X, right? Now according to the coupling, we are going to get something here. So your first two are going to be destabilized by similar energy, and second ones are actually going to stabilized. So it is something like this. Could have been here, it could have been here, but it is stabilized. Similarly for this, it could have been here, but it is stabilized. It is destabilized, right? So these factors are all same. It may not look same due to my poor drawing skill, but all these factors are HJA by 4, right? HJAX by 4. So this is your changed energy, but still what is going to be the gap between E2 dash minus E1 dash? What is the new gap going to be? It is something like what was there earlier. It has been destabilized, the second energy level, right? Hx by 4, and the second one is destabilized. So it was plus, but ultimately minus Aj by 4. So the energy gap has been E2 0 minus E1 0 minus Aj by 2, which is nothing but this part was nothing but H nu x, because it was associated with the spin flipping of the X nuclei, right? Minus HJAX by 2. You can show that. And what about these two? And what about uh, E3 dash minus E1 dash? Similar, right? E3 not, it has also been stabilized, and the second one has been destabilized, but as minus was there, so plus become minus. So eventually there is the gap between E3 0 minus E1 0 minus AJAX by 2, and this gap was nothing but the spin flipping of A nuclei, so H nu A minus AJAX by 2, and this is one condition. And what about the gap between E4 and E3. Earlier it was associated with a change in the spin between the X nuclei. So it would be similar. It is actually increased by age. The fourth is actually increased by this amount, and what is the energy? This is actually destabilized, right? E3 is 0. Destabilize minus minus plus m x by 4. So you are going to see this gap is x by 2. So this is actually earlier it is associated with mu x by 2. Similarly, for E4 dash minus E2 dash, which was earlier associated with the spin, now also the spin flipping of A to B, so that you can show it would be H nu A plus H x by 2. So in the spectrum, so earlier this was the case, right? Here new x was here and new A was here, right? But right now what you are going to see that you around the new x you are going to get two spectra related to the flipping of spin of the nuclei A. One coming at 8j by ax by 2 energy and another at 8jx by plus 8jx by 2. So one you are going to see here and another here. The gap is going to be the same. This is in frequency scale, so I remove the h, right? X by 2, x by 2, overall gap is jax, right? Similarly, for new A also, we are going to get two spectra, right? One would be, and the total gap would be, I will not write much, jax by 2, right? Sorry, jax. Anyway, so due to coupling, what you have seen that your both due to coupling of x, effect of x on A is that your intensity has halved, because earlier your intensity, both the intensities are coming from, so it was added up because there are two transition related to the spin flipping of A, but the energy was same, so that's why it got added up. But now what happened that the two, due to the coupling of x on A, what happened that your two transition become distinct, and one at uh, plus scale and another at minus scale, right? So this one at plus and this one at minus, this one at plus and this one at minus. So okay, so this is how you are going to see a system for uh, AX kind of splitting. But now let us go to another system, which is A2 kind of system. In A2 kind of system, what is happening? What is going to happen that you will expect it to be uh, equivalent. So you don't expect that there should be some coupling. But let us see what is actually happening. This means two nuclei are, very sorry for that, nuclei are equivalent. Okay, so we are going to see if they are going to affect on each other or not. Okay, so right now as you can see, the both are having a shielding constant of sigma a, right? I'll write it, the Hamiltonian, but we can define it as Iz1, 1 and 2 are different, two nuclei is different, but they are they are same nuclei. If they are proton, they are both are proton, but they are also equivalent, but we are marking them as 1 and 2, but we, as they are equivalent, we can't really distinguish between them, and that is going to be a bigger factor here when we write the wave functions. As we can't distinguish them, see, we will write, so one will be like previous alpha 1 alpha 2, another will be beta 1 beta 2, but we can't now write one will be alpha and two will be beta, because we can't distinct. So we have to write these normalized wave functions as alpha 1 beta 2 minus alpha 1 alpha 2 beta 1, and another as 1 by root 2 alpha 1 beta 1 plus alpha 2 beta 1. So this is the effect of, as we can't distinguish between them. So let us see what is the energy levels. Energy of the first one, alpha 1 alpha 2, is going to be minus gamma b0 1 minus sigma a iz1. Okay, so I am writing it twice. I will actually making sense here. So energy of the unperturbed system when alpha 1 alpha 2 is, I will write this term outside the integral. Now I'll write the rest of my part of Hamiltonian. I have written it wrong, it is not B, it is equal to A, okay? And this is I Z2, and then alpha 1 alpha 2. Okay, now this is going to be simple, and like the previous one, we'll split it. So I can also write this term outside. IC1 operating on I alpha 1 alpha 2, and then gamma B01 minus By doing this, I am increasing my writing. Actually, I didn't have to do this much, right? I missed some part. Okay. So the first part is going to IZ1 will going to operate on alpha 1 and it will give me h cut by 2, right? So I'll take that outside, h cut by 2, 1 minus sigma a, and then this is going to be 1. What about this? IZ2 operate on alpha 2 and it will give me same h cut by 2, 1 minus sigma a, and that makes me gamma b0 h cut 1 minus sigma a, right? What about similarly you will be able to show that beta 1 beta 2 unperturbed energy is same but with a positive sign. Why? Because it is beta 1 beta 2. So beta 1, when you operate Iz on beta, it will give you a minus beta. So you are going to get this minus thing, and that is why you are expecting that you are going to get I0 1 minus sigma. Okay, this is going to be your energy for the unperturbed fourth in A2 system. Now we'll see what is going to be the energy, unperturbed energy in case of each of the system. This is going to be interesting. So minus gamma b0, we have 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1. Then actually I can take this as this is going to be a common thing. So I will take the shielding constant outside. So I have to write this. And both will contain 1 by root 2. So I will keep it here. First we'll have alpha 1 beta 2 plus beta 1 alpha 2. So better to write in a same manner alpha 2 beta 1. Then I have IC1 operate on this. Similar thing, I have another part alpha 1 beta 2 plus alpha 2 beta 1 IC2 is there, right? Alpha 1 beta 2 plus alpha 2 beta 1. And the first thing we see that gamma b0 1 minus sigma a 1 by 2, and then IZ1 will work on alpha 1 and it will give h cut by 2 alpha 1 beta 2. It will not work on beta 2, right? Next IZ1 will work on beta 1 and it will give h cut by 2 but minus alpha 2 beta 1. Okay, so alpha 1 beta 2 minus h cut alpha 2 by, so what you can do is that you can take, I will not do that for the step, I will not do the step chart right now, and the next term will give you gamma b0 1 minus sigma a IZ2 will work on beta 2. So at first you are going to get alpha 1 h cut by 2 minus beta 2. On the next one you are going to get h cut by 2 alpha 2 beta 1. So what you are going to see that your these are not anymore eigenvalue equation on the by the operation of, so these have become orthogonal. So what I'm trying to say, I will just write one line maybe here, 1 minus sigma. Before that, let me stay on the call, or this is call. I hope this is last. Anyway, thank you. So 1 minus sigma again, and h cut by 2, I can take it outside. So, and 1 by 2, I can again put that inside because these are the normalized wave function, right? Alpha 1 beta 2 plus alpha 2 beta 1 multiplied by 1 by root 2. But now what has happened that it has become alpha 1 beta 2 minus alpha 2 beta 1. See? So this is going to be 0. Similarly, gamma b0 1 minus sigma a h cut by 2 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1, and this side you have 1 by root 2 alpha 1 beta 2 minus here plus here alpha 2 beta 1. This is also not a, this is also orthogonal situation, so you expect that this is going to give you 0, this is going to give you 0. So as a result you are going to get 0 total. So your E30 is going to be total. Similarly, you will be able to show that your this energy. So right now you don't think about what is E30. Those are actually equivalent. Right? This is equivalent. So what I'm trying to say, when no coupling energy of the spin states are as follows. You have beta 1, beta 2, alpha 1, alpha 2. And these two are degenerate states with alpha 1, beta 2 plus minus alpha 2 beta 1. Okay? So these having an energy of 0 and these having an energy of minus gamma b 0 h cut 1 minus sigma. Anyway, so now you will see what is the gap between them. So this is your fourth, two or three together. This is your unperturbed one. So we can consider only, we cannot go from alpha 1 alpha 2 to beta 1 beta 2, only we can go to these states. So the gap So what are the transition are possible now? So alpha 1, alpha 2 to this one. Obviously these are of similar energy and these two. So, but as you can see, all these energy gaps that E04 minus E0 3 0 you are going to see as this is 0, so it is going to give you a value of gamma B0 H cut 1 minus sigma A. Similarly, when you look for the energy gap between these two 3 minus E10, you are going to get same value, and which is actually equals to this. And that's why in the spectrum you are going to see only one line consisting at the Larmor frequency of this A nucleus. Even though there are four transitions are taking place, we are only seeing one. Okay. Now we will see that what will be the effect of coupling. Okay. So obviously coupling will act as a perturbation. Okay. So here you again your coupling Hamiltonian is going to part of Hamiltonian is going to be H by H cut square J A now, and it is going to be I1, right? So obviously your first order correction to A1 is going to be H by square J A, right? It is alpha 1, alpha 2. Now this is going to be X1, X2 on alpha 1, alpha 2. So I have splitted these into three terms, right? Because your I1, I2 vector scalar product of that is going to be I1, I2, obviously X is going to be there, then I Y1, I Y2 plus IZ1, IZ2, alpha 1, alpha 2. Obviously, the third term is going to be, so these are the hat sign what I am giving for operator. So this is the first term X. When it is going to operate on alpha, it will give you beta, so ultimately this will lead to 0, right? So this is going to lead you to 0 as from our earlier thing. Also when IY will operate on alpha or I will operate on alpha, actually this is going to give you beta, so this is also going to give you 0. But In these cases you are going to get something. So that is alpha 1, alpha 2. IZ1 working on alpha 1 will give you h cut by 2 alpha 1, h cut by 2 alpha 2, and this is going to be h a by 4. So alpha 1, alpha 2 is going to, again, like the previous case, destabilized by HJA by 4. Similar treatment, similarly, be able to show E411 is going to be HJA by 4. That is beta 1, beta 2 is going to be stabilized by JA by 4. What about the in between terms? This is where the calculation will become very, very interesting. So it is h by h cut square JA is 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Then it is I x1 I x2 operate on 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Then the next will be h by h cut square JA. It is IY1 IY2 and the third term. Okay. Now let's see what each term will give us. H by h cut square JA multiplied. Now 1 by root 2, 1 by root 2. I'll not do anything right now. I will keep them as it is. But what will alpha x1 will work on alpha 1 beta 2? I will just write 1 by root 2 here. So alpha 1 beta 2, what it will become? So x1 will operate on alpha 1, x2 will operate on beta 2. So x1 will become h cut by 2 beta 1 and hx2 on beta 2 will be h cut by 2 alpha 2. What about the next one? It will become h cut by 2 alpha 2 h cut by 2 alpha 1. This is the first one is done. And what will be the next one? H by h cut square JA. IY1 will work on alpha 1 to give you IH1 by 2 beta 1. IY2 will work on beta 2 to give you minus IH cut by 2 alpha 2. IH cut by 2 beta 1 multiplied by minus IH cut by 2 alpha 2. Similarly, the next one would be alpha 2 would be IH cut by 2 beta 2, and minus I will write it here IH cut by 2 alpha 1. What I have done, that minus IH cut by 2 I have just multiplied here, minus minus plus. Now the third term, it is going to be 1 by root 2 IZ2, this is going to be Z. So H cut square by 4 alpha 1 beta 2, as it is beta is there, so it will be minus, right? And minus minus plus will be here, H cut square by 4 alpha 2 beta 1. They are not going to change the value. So for the first term, again we have to go and see what are the things we have. We have H cut by 2, H cut by 2. I will write it maybe last time. Alpha 2 beta 1 minus, I have made some mistake here. The first one should be beta 2. Alpha 2 will become beta 2. Alpha 1. So what I will do, I have to do a step jump here. See, H cut is by 4, I can take a common. I can take minus H cut square by 4 as a common. So it will become, so if I take minus H cut square by 4 as a common from here, minus H cut square by 4, then it will become alpha 1 beta 2 minus alpha 2 beta 1. So overall this is going to be a normalized case, so it will give you 1. What about the next case? H by H cut square Z A. So I have given this space because you understood already that I am going to take something common. 1 by root 2 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, then 1 by root 2, and this has become, so this is the part which we are talking about. So IH cut by 2 multiplied by minus IH cut by 2 minus I square, which is plus 1, so it is H cut square by 4 alpha 2 beta 1, and this part would be minus H cut square by 4 alpha 1 beta 2. So you understood that I have to take minus H cut square by 4 common here also, and if I do that, I'll remove this, and I have to change the sign. It will become plus plus, it will become minus, and it is again become alpha 1 beta 2 minus alpha 2 beta 1, and it is now and you need to consider 1 over root 2 inside this, because this is a normalized wave function, right? So then only it will give you 1, and then the last term, so that is your, again I will go here, 8 by 8 pi square JAA 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1 1 by root 2. Obviously I can see if I take common minus h cut square by 4, then it is going to be my alpha 1 beta 2 minus alpha 2 beta 1. As you can see, these all are actually not 0, but this is 1, this is 1, and this is 1. So I am actually getting minus 3h cut square by 4 h into h cut square JA, which is nothing but minus 3h by 4 JAA. So this 1 by root to this spin state alpha 1 beta 2 minus alpha 2 beta 1 is going to stabilized by 3JA by 4, this term. Okay, now we have to consider for the next row, that is another state which is your h over h cut square JAA 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1, and this is I. You can just do the calculation without saying much, just follow what I'm trying to do here. Same thing as previous, but there will be something different, that is why I'm doing, or else I would have told you that similarly we get something here. See, Ix1 is going to operate on alpha 1, Ix2 is going to operate on beta 2. The same thing we are going to say. When X1 is going to operate on alpha 1, you are going to get h cut by 2. Actually, if you consider both, you are going to get h square by 4, but the sign will change, right? It will become, no, not the sign, but the wave function will change, beta 1 alpha 2. Same for the next part. It is going to be beta 2 alpha 1 sine. The functions are going to change, but the sign will remain same. Now as y has come, that IH terms are going to come when working on alpha. There will be no minus. When working on beta, there will be minus. So as you can see, in both the cases, I am going to get one time IH crossed by 2 and minus I crossed by 2. So it will lead to me actually H squared by 4. And as the sign will change, I will directly write this. As the minus is not here, so that's why the calculation is little different, right? And this part is easy, no change, but here will be a minus sign because beta is there. So here actually what you are expecting, in this term you are actually taking out h cut by 4, next also h cut by 4, but here you are taking common h cut square by minus h cut square by 4. Okay, you are taking something like this. So this is 1, and that is, and you are going to cut 1. So ultimately you are going to see you are going to get something like this. So even though your that state minus state is going to stabilize by 3 times of this, it is actually getting destabilized. Due to this, how your spectrum will look like or the energies will look like, I will draw them. So earlier, so this was the case, beta 1, beta 2, and these two states were degenerate. This was, now what happened, this has actually destabilized, this has destabilized by J A by 4. Same for this. Similarly, this third one is also getting destabilized by HA by 4. But this third one is actually stabilized to this, actually earlier your spectrum was like this, four spectrum fall on the same place. So you expect, in this case you expect at least two different kind of spectra, right? But let me give you the energy balance. This is your dash, 3 dash, 2 dash, 1 dash. So energy gap, new energy gaps are now E4 dash minus E3 dash. Stabilized. So this has not changed, which is actually equals to this. What about E4 minus E2? It is actually changed. I guess you can see this. What about E3 dash minus E1 dash, which is related to the same spin flipping thing? The gap between these has not changed. It is there on the same. So you expect some coupling, but here comes the fact, as you can see in your electronic states, and one additional selection rule will now come into the place, that is your delta S should be 0 for the allowed transitions, right? So this was not the in the case of AX system, because those are distinguishable spins. But now, as here your spins are indistinguishable, you can see only one state, that is alpha 1 beta 2 minus alpha 2 beta 1, that is now your antisymmetric, and that is singlet state, and the others one are triplets. So only allowed are triplet state. See here, whenever the second state is there, the transition is not going to take place. So as you can see, the transition, those are allowed, still have the same energy gaps even after destabilizing, because they have destabilized to the same amount. So in the spectra, you are not going to, so there is, so I will use another color. So there is So with that, we will today we will stop our theory sessions. I hope this was beneficial because I guess the slides are not visible in the lecture video. So I hope you can use these as your notes. I hope the writing at the end. I was in a hurry, so I hope it is still readable and you can take this as a note, right? We'll just solve a few questions from the assignments and then we will stop. And the first question is the NMR spectroscopy used for determining the structure in which of the following materials: radioactive, insoluble chemical compounds, liquid, gases. Obviously the answer is liquid, but let me give you another answer that insoluble chemical compounds or suppose solid compounds you can also do at solid state NMR. Okay, so if you are given a MCQ question where you're only one to this circle kind of question, then you choose only for liquid. But if you are given a MSQ question of the same question, then you also have to select insoluble chemical compound. Solid state NMR is also possible, right? Okay. Now the second question, NMR spectroscopy indicate the chemical nature of what and special position of what. Obviously NMR spectroscopy will give you the special chemical nature of your nuclei and obviously give you idea of the neighboring group, right? Due to which the deshielding or shielding, what kind of electronic environment is there. So question number 3, the amount of energy available in radio frequency in the radiation is sufficient for which of the following? Obviously affect the nuclear spin of the atom, that to split, right? That to change the spin, flip and right, and which each of one chloropentane 2 in shows largest chemical or downfield shift in the NMR spectrum. It is actually, I will give you the structure. 1 chloropentane, so 5. So this is 1, this is second, this is number 2, in group is there, 2, 3, 4, and 5. These are actually carbons. I am not marking the hydrogen, so there are hydrogens, 1 each. There are 2 hydrogen, there are also 2, here 3 hydrogen. So actually these 2 or 3 position actually they are going to be much deshielded, okay, due to this the double bond is there. If you see the characteristic chart, you will get that idea. Now we are going to actually discuss this question as the last question because we have not discussed the 180-degree or this 90-degree pulsing. So maybe I can take another class maybe, or I'm not sure about that. But obviously the lectures are good enough but to answer those questions. But let me answer this question: which of the following statement regarding the NMR spectroscopy is wrong? The first question says the NMR signals towards the left of the spectral chart corresponds to a larger chemical shifts. Obviously this is correct. Then chemical shifts are larger when the frequencies of the radiation, which includes the nuclear transitions, are higher. So shift will be higher when the gap is higher, obviously. Now this is also correct. Now the third question, third option is chemical shifts are larger when shielding effects are greater. No. When the shielding is larger, then your energy gap between the spin states are going to less. So chemical shift will be less. So this is actually the wrong statement. So this is what you need to say. The fourth one also we will discuss as hydrogen signal is split into n plus 1 peaks by spin-spin coupling when the number of equivalent hydrogen in that direction is n. Obviously you know this and no other neighboring atoms are involved. Obviously you know this and we use this in the interpretative molecular spectroscopy or interpretative NMR spectroscopy. When we try to interpret this, where how many protons are there in the neighboring signal, we can get an idea from this spin coupling, right? It is going to be singlet or triplet depending on the Pascal triangle, right? Okay, so with that actually we don't have any more question. So I hope that the whole live session, this things we are going to actually end here. This is week 12. So with that, actually I'm thanking you for listening to this discussion sessions, and I hope this was beneficial for you. And with that, today we are going to end this session, and thank you very much for listening. Thank you very much.